Hi my friends, today we discuss about finite element analysis, a very interesting domain of mechanical engineering, which is fully supported by Inventor. This picture shows you what are the possibilities of finite element analysis. You can consider this module in Inventor viewing from three directions: analysis, load, and subject. Analysis can be static, model, and shape generator. Load may be force, moment, or pressure, and subject are parts or assemblies. This means that you can combine all these possibilities in different analysis, and we count here 6 possibilities and here another 6. So the possible variants are 6 multiplied by 6 mean 36 variants. And this one, which is a special kind of finite element analysis, where you can start with a part and you finish with a new shape of the part, and this is the generative phase of the Inventor, because you start with a part and you finish with another one, a solid of equal strength. We start by creating this 3D lever. The lever is pretty simple. As you can see, it has 2 arms and the possibility to be fixed here, and another to place here a force. Having we have the dimensions, and we start by opening the standard template. This is the plane with X to the right, and we start from somewhere by creating this contour. You see tangent, tangent, tangent. Here is not tangent. We add a tangency here. Okay. We constrain this point here. Let's apply 80, radius 10, and radius 15. 80, 10, 15. 80 is from the left arc to the right arc. 80. 10 and 16. The only dimension needed is to have these 2 points on the same horizontal. Then 6 is the thickness of this part of lever. Extrude 6. Okay. We can start from this and to use 6, and we decrease the height with 6. So create a sketch here, finish, and extrude 120 minus 6. We don't invent dimensions. We create a sketch on the top, and looking to the drawing, we see something very interesting. These two lines are symmetrical about this axis, and this axis contains a line which is placed at 6 and so on. This means that we have to constrain these two sides to be symmetrical about the line, and the line to be vertical and coincident with this center point. We use all the information in the drawing. We don't have here a dimension, yes, but we assume that these two lines are symmetrical. We draw two tangents, not tangent, but no problem, to here, here, and a tangent. So we place a tangent here. This line must be horizontal. Now it is, oh, these two were perpendicular. We have to eliminate this perpendicularity, delete, and now horizontal for this line. This line must be vertical, and it is vertical, and also perpendicular with the other. Good. And now coincident this line with this point, and symmetry between these two sides and the vertical. Okay. Now we place dimensions. This is 130, this is 10, and this 6. That's all. 6. Fully constrained, as you can see. Home, finish, and now extrude this the other direction on 6. Okay, now only holes are to be added. What holes? This one of 16 and other 3 of 10. Let's start with this one. Place on the face, concentric with this, and dimension diameter 16. Plus on this face, concentric of 10. The other two are placed on these faces, so we have to remember 30 and 30 and 30 and 40. This is with 30. We place a point somewhere here, we ensure the position. Oh, this is why we have always to keep horizontal, to have in our mind which is the horizontal, because when I place horizontal, I am sure that this is okay. The dimension is 30. Finish sketch, hole, 10, okay, and 40 here. This is horizontal, so I have to be sure. A point here, vertical with the center, and 40 is the dimension. 40. Finish sketch, hole, okay, material, steel carbon, gunmetal, and we select some faces to make them titanium polished. Also this, I keep the key shift pressed during the selection and apply titanium polished. Okay, now we activate environments, stress analysis, and as you can see, no icons are enabled. Why? Because we have to create a study, a new simulation. For the moment, static analysis is okay. Let's apply the static analysis, not model, not shape generator. Okay. Now we have to create settings for assign, for constraints, and for loads. These three, 1, 2, 3, are compulsory. Assign is about material. The material is steel carbon. If here is a generic, we have to change it to some material. We don't have to do anything here. Okay. Next is to apply constraints, and we choose pin on this hole, which constrains on radial direction and axial direction, not tangential. This is remarkable. You have to remember this. Apply. You see here a so-called glyph, and we apply another constraint, the same solution, pin constraint on this hole. Okay. The last is a force which we want to be applied on this face in this direction with the value of 350 newtons. We can write here 35 decanewtons, yes, to be almost 35 kilogram force. And now Since we fulfilled all the requirements, we can start to apply finite element analysis. We use this tool which calculates for us a great amount of data, because you know that this method creates a discretization of the part, and every discrete element is in connection with all the others. We can see this by using the mesh view, which will show us that elements we'll discuss about. Now we see that something happened here, and some colors are presented together with a scale, and we see that the results are concentrated on the first variant of this analysis. In fact, von Mises stress. The units are megapascal, which seems to be pressure units. They are not pressure, but they are tension, because the same units can be used in both situations. The maximum is 70 and 70 megapascals, which is not so important, but it is a value. Nowhere we see red. This means that this value is somewhere inside the part and not visible. We can animate this image, and we can see how this happens. You can make also changing of the view to see where is the part most solid, most stressed. Okay, but this is an exaggerated presentation, because if you choose actual, the actual deformation and actual really situation, you can see that the movement is not so dramatic. Look here. Yes, you see that a small amount of bending happens. More than this, instead of von Mises stress, you can choose displacement as the result, and the animation will show you where is the greatest movement, the greatest displacement, somewhere here. Of course, this part is fixed here, and only this arm is displaced. You can choose this maximum value, and you see where is the maximum value, And this is very interesting, because this point is with the maximum value. And where is the maximum stress? We go back here and we apply animate, and we see that the maximum displacement, the maximum stress is somewhere here. We can also see a small change, something we didn't see. This is the point with red. Only this point. You can apply another element, like the changing the constraints. For instance, we can remove this first constraint, which is the movement along this axis. We delete this constraint, and we add another pin on this hole. Okay, now we simulate again, and we see some important changes. Now the value is 395, and animation will show us, but not actual, but like before, to have a level of comparison. Animate, you see the great movement of this point. If we go here, we have a maximum of 1 millimeter displacement, which is relatively important. Going back to the stress and looking around this hole, we can see that this is a very great stress around this, and we can change the part in order to reduce this stress. Let's do it. Let's enlarge this highness or thickness of this arm. Okay, go back from analysis to the part, and extrusion, first extrusion, double click, we change 6 with say 8. Okay, and now go back to environments, stress analysis, we verify that loads is applied, the value is as before, and also the other elements. So we can try to see what happens in that zone. simulate, we see that the point is moved here, but the value is slightly smaller. Yes, 265 against 395. Now we want to see the discretization, the mesh. Click here, show us the mesh, and we can make a profound analysis by changing the density of mesh around this point. We do this by using mesh settings. Now the average element size is 0.1 watt, 0.1 millimeter, and you can change not all the elements. You can do this by applying here another value, but to go to a local mesh control, for instance this circle, where we want element size not 0.1 but 0.05. Okay, we have to generate again the simulation. When we change mesh data, we have to change this, and now you see a very dense, a great density around this circle, showing us what happens in this zone. I hide the mesh, and we animate again, and we see that this zone is the most solicited. There are a lot of possibilities to study all the implications of such an analysis. But this is enough for today. We'll go back to other variants of analysis by using finite elements in the next tutorials. Bye bye.